Hi there, and welcome to this lesson. Now, in this lesson, we're learning about surds, okay? And under surds, we'll be learning about the basic forms of surds. And at this point, I'd remind you to set the video to play in 1080p HD. Okay, you can do so via the settings icon on the bottom right. And as the lesson progresses, if you have any issues at all, or if anything comes off as unclear, please feel free to get in touch. All right, you can do so via the course dashboard. Um, yeah, I think we should jump right into the lesson. So surds, the basic forms of surds. What are surds exactly? Okay, what are surds? I believe a few of us may have come across surds before, but what are surds really? Now, to understand surds, we need to understand surds and numbers. I'll tell you that. To a special type of numbers, and to understand surds, we need to understand rational and irrational numbers. Okay, we have two kinds of numbers. We have rational and irrational numbers, and we need to understand what rational numbers are. Now, a rational number is a number that can be expressed as the quotient or a fraction of two integers. Now, if you don't know what integers are basically your regular numbers. So 1, 2, 3, 4, 5, 6, no decimals, just the numbers, your countable numbers. For example, if I told you to count from 1 to 100, the numbers you count. They also include negative numbers as well. So -1, -2, -3, -4. So your whole numbers pretty much. And a rational number, just think of it this way. A rational number is a number that can be expressed as a fraction. For example, if you is as a fraction of two integers. For example, you have 0 0.5. 0 0.5 is a rational number because you can express 0 0.5 as 1 over 2. Okay? Another rational number, here's a good example. An infinite number, okay, 0.333333 is a rational number because you can express that as a fraction of two integers, i.e. 1 over 3. Okay, so a rational number is a, let's say, a sensible number. In a way, you can think of it in that manner. It's a number that makes sense. Okay, just think of it that way. And then examples of rational numbers, like I said, you can have 2, you can have 1 over 2, you can have 0.28, you can have a decimal. A decimal number can be a rational number because if I ask you to express 0.28 as a fraction, you'd basically tell me 28 over 100. You can simplify that out and you eventually end up with 7 over 25. So that is a rational number. Okay, now let's talk about irrational numbers. And irrational numbers you can consider as numbers that really don't make any sense. Okay, just think of it in that manner. All right, now an irrational number is a number that cannot be expressed as a ratio between two numbers or written as a fraction. Now think of it in this manner. An irrational number you can never express as a fraction, and usually they are infinite numbers. All right, they're usually expressed as decimals, infinite decimals, and you will never be able to express those decimals as fractions. I'll give you a good example. And a good example is pi. Now pi is 3.142 something something something. It's actually infinite. Okay, it doesn't stop. All right, and 22 over 7 isn't exactly pi, it's just an approximation. All right, we really can't express pi as a fraction in its actual sense. Basically, another good example is e. And basically we use e is Euler's number, and we use e when we work in natural logarithms. And e also is a decimal, and it's also infinite, and we basically cannot express e as a fraction. Okay, and we also have root 2. I think if you find the square root of root of 2, I think you have 1 point I think was it 1.7 something something something, and it goes on it goes on basically, and you really can't express this root 2 as a fraction, as a definite fraction of two integers. So these are what we call irrational numbers. Now, surds are irrational numbers, okay, but a special type of irrational numbers, because surds are irrational numbers which are roots of rational numbers. So just from the example that we had before, root 2 is a surd because 2 is a rational number, and then when you find the square root of 2, it gives you an irrational number. Okay, it gives you an infinite number that can't be expressed as a fraction. So what other surds do we have? Basically, we have root 2, the cube root of 7. Okay, it doesn't necessarily have to be a square root. It could be a cube root or fourth root or a fifth root. So we have the cube root of 7. If you try to find the cube root of 7 with a calculator, it would not give you an exact number. It would give you an infinite decimal rather, which cannot be expressed as a fraction. And then the fourth root of 19 is pretty much the same. So this is what surds are. Surds are irrational numbers which are roots of rational numbers. Now, surds, which are square roots of rational numbers, okay, so like I said, you can have square roots, cube roots, or fourth roots, but then when you're talking about surds which are square roots of rational numbers, we call these quadratic surds. And basically that would be talking mainly about quadratic surds in this lesson, and pretty much all our lessons on the surds will basically be turning our focus to quadratic surds. So there are certain properties of surds, some things, just some very minor things that we need to take note of, okay, if we're going to do any operations on surds. And then the first thing we need to know is the distributive property of surds. Now, we already talked about distributive properties. We did that when we're doing indices, okay, where you have if you have 2 multiplied by 3 all to the power of x, it basically equals 2 to the power of x. You can basically assign that x to 2 and assign that x to 3, okay, and then it's pretty much the same thing here. If you have a surd written like this, so you have a surd as the square root of 5 times 2, you can assign the square root to 5 and then multiply by the square root, assign the square root to 2, and basically you have root 5 multiplied by root 2. And this is works with multiplication, and just like indices, and it also works with division. So if you have the square root of 5 divided by 2, it equals the square root of 5 divided by the square root of 2. Something very important to take note of: the distributive property does not apply when you're dealing with addition, okay? So if you have the square root of 5 plus 2, it does not, and I need you to pay very close attention here, it does not equal the square root of 5 plus the square root of 2. This pretty much can't be done, okay? But we would be addressing this later on in the lesson. All right, now basic forms. So what are basic forms? Now consider the surd root 50. Now root 50 is a surd because you can't find the square root of 50. If I ask what's the square root of 50, you can't find the square root of 50. You can find the square root of 49, but yeah, you really can't find the square root of 50. So root 50 is a surd. But then there's something special about the surd in that it can be simplified, okay? And how do we go about simplifying this surd? Now think about it. 50, something special about 50. 50 is 25 times 2, okay? So basically root 50 is root 25 times 2. Interesting. Now, based on the distributive property of surds, I can actually have root 25 times 2 as root 25 times root 2. Okay? All right. And then root 25 is 5. So I have 5 times root 2. Okay? So 5 times root 2. And in mathematics, we simply write it as this. 5 root 2. Just like we have 5 times x is 5x. We have 5 times root 2 is 5 root 2. And that's the idea. That's basic forms. Okay? Now basically we had a surd root 50, and basically we're able to simplify simplify this surd because we realize that there is a perfect square in 50, i.e. 25. Okay, and once you have a perfect square in 50, i.e. 50 can be divided by a perfect square, you can divide 50 and get a perfect square. You pretty much just try to extract that perfect square and you simplify as I've just shown you. Now, let's do an example. Example 1. And example 1 says express root 54 in its basic form. Okay? And this is actually really easy. We just need to follow the steps that I just showed you. So step 1. Now we have root 54. Now can you think of a perfect square that root 54 can be divided by? Think of a perfect square. Okay, let's consider perfect squares. We'll start with 4. Okay, we'll start with 4. 4. I don't think 4 can go in here. No, 4 wouldn't work. And then 9. Okay, yeah, 54. I think 9 would work. And basically 54 is 9 times 6. So I have root 9 times 6. And basically this becomes root 9 times root 6. And when we break root 9 down, we have the root square root of 9 is 3. We have 3 times 6 and it gives you an answer 3 root 6. Simple. That is it. That is how you express a surd in its basic form. Let's go for another example. So example 2. And example 2 says express 180 in its basic form. Okay? Quite simply, 180. Now, there's a perfect square there. Okay? And basically, if you keep trying the squares, you start with 4, 9. Okay, you can actually use 9, but then you usually aim for the largest square number that you can divide 180 by, and I'll tell you that that square number is 36. Okay, because when you have 36 times 5, it'll give you 180. 36 times 5 is 180. So basically you have 36 times 5, and that based on the distributive properties of surds, you have root 36 times root 5, and root 36 is 6. So you have 6 times root 5, and you have a final answer 6 root 5. Okay, let's go for another example. Example 3. And example 3 says express 7 root 2 as a single surd. Okay, so in this case, basically we've been changing single surds to basic forms. Okay, now we're going from a basic form to a single surd. Okay, so in a way we're expanding this. All right, and quite simply, you have 7 root 2, 7 root 2, and you can write this at 7 times root 2. Okay, and basically you have 7 there. 7 is root 49, so you have root 49 times root 2. Okay, so you square the number, square root, so 7 is root 49, so you have root 49 times root 2, and based on the distributive properties of surds, you have root 49 times 2. Okay, and that would be root 98. And that is how you convert a surd in its basic form to a single surd. And that would be it for this lesson. Okay, and in the next lesson we'll be learning how to perform certain operations on surds. All right, and you learn there is a small similarity between surds and algebra. All right, and basically you can see we use, like, just like you have 7 times x, we write 7 times root 2 as 7 root 2. Okay, 7x. Okay, and yeah, bye for now.